Thank you, Christian, for the introduction. Hello, everyone, and thank you for joining the session. This work is an outcome of a collaboration with Netflix, with Kyle Swanson, Mariana Afonso, and Joel Soul, and my colleagues from the University of Bristol, Fan Zhang and David Bo. And the topic is on a novel method on estimating efficiently a VMAF-based bitrate ladder for video adaptive streaming. As well known, video content is very diverse within its parameter space. As you can see in this example here, we have 100 different sequences with different colors, different motion patterns, different spatial information, with different static or different dynamic textures that result in a very variable compression performance. On top of this, we have users that are on slow or fast networks and that use different devices. They use phones, they use laptops, they use TVs and any other devices they have. So the aim, of course, is to keep everyone happy and deliver the best possible quality at the target bitrate. In HTTP adaptive streaming, video content is conventionally encoded by adapting its spatial resolution and quantization level to best match the end user. A set of combinations of resolutions and target bitrates is created, like the example shown here from the Apple Tech Note, and that is what we call bitrate ladder. It is well known that the traditional solution of using a fixed bitrate ladder for all content for every video does not result, of course, in the highest possible quality. And we can definitely say that one ladder does not fit all. Recently, content customized solutions have been reported and adopted by the industry, such as those used by Netflix, Bitmoven, Brightcove, Vimmer, and more. Some of these solutions are based on exhaustive encodes and others on probe encodes to conduct complexity analysis and then decide on the basic parameters to use. You probably all remember that one of the best solutions that was proposed by Netflix was the per title, let's say, customization of that bitrate ladder that resulted into something like this, which verifies the need to have a content customized solution. Now, if you want to find the optimal method, the optimal ladder, the way to do it is to do an exhaustive encode across different resolutions and across different parameters. But that then means that we will have a high financial cost, but also a high computational cost, which costs also time. So the question is, how can we find the best bitrate ladder per content so that we don't need to compromise first the quality of experience? And at the same time, how can we make this process computationally efficient? But let's first define a bit better what a bitrate ladder is. The initial step in constructing generally the bitrate ladder is to select the target bitrates at which we want to transmit our videos. And those will represent what we usually call the bitrate ranks. The VMAF ladder can be defined as a set of tuples L that comprise bitrate values RL with the associated VMAF values VL, the quantization parameter QPL, and the resolution SL. Of course, the resolution, the quality, and also the bitrate, they have to be monotonic. What we do is we extract the Pareto front, as we said, and then we sample this by using the set of target bitrates RL. We sample across the rate dimension, and then consequently, we sample across the quality dimension. We check if it is meaningful to retain all ladder ranks by checking the slope of the VMAF rate curve and by seeing whether the change in the VMAF value is meaningful in order to keep, let's say, adding ranks on our ladder. Let's have a look at several different methods to build the reference ladders. As explained before, if we want to build the reference ladder, we need to do an exhaustive encoding across the resolutions and across the range of the QPs, and then compute the Pareto front, and then sample the Pareto front and extract the bitrate ladder. Another way to do it, which we have used also in our previous work, is to use naive interpolation. So instead of actually encoding all the QP across the whole QP range, what we do is we take equidistant steps and equidistant QP values across the different resolutions, and then we interpolate based on those encodings, and we extract the Pareto front. And based on that, we can build the bitrate ladder. Here we propose, in this work, we propose to build ladders using content-driven interpolation. Instead of using the whole range of QPs, we drive the interpolation towards the part of the curve that are closer to the Pareto front. So what we actually do is we find where the saturation on the VMAF curve happens by computing the knee points of the curve. The knee point is the point of the highest curvature. If we were in the continuous domain, this problem would be easier to solve by using this formula over here. But because we're in the discrete domain, we need to find another way to define and estimate the highest point of curvature. For this purpose, we use the needle algorithm as described in this paper over here, and we compute the knee points of the curves across the resolutions. This algorithm is based on the notion that the points of maximum curvature in a dataset are approximately a set of points in a curve that are local maxima if the curve is rotated clockwise by an angle defined by the line that connects the lowest and highest values in the dataset. Now, if we check the knee point distributions, the points of the highest curvature, let's say, that correspond to which QPs they correspond, you can see that the distributions are quite tight around the mean values. So, for example, for the 4K resolution, we have the mean knee point around the 30 QP, while for the 1080p resolution, the knee point is around 25. And for 720, it's quite close to that. And then for 540, it's a bit lower. It is also important to note that although the knee points of the high resolutions are part of the Pareto front, as you can see over here, usually the points of highest curvature at lower resolutions are not typically included in the Pareto front. This means that if we want to actually guide the interpolation, the range of the interpolation, we need to shift it lower to the lower resolutions. We need to shift it towards, let's say, higher QP values, while for the high resolutions, we need to shift it towards lower QP values. Considering all this, the proposed method predicts the highest curvature point of the RQ curves to guide a small set of initial encodes closest to the Pareto front. After encoding, a piecewise cubic Hermite interpolation is applied for the interim QPs, and based on those values, the Pareto front is extracted. This method produces a suboptimal solution, of course, but its accuracy depends, of course, on the number of the encodes performed per resolution. The added benefit that we saw with this method is that by adjusting the number of encodes, you can increase the accuracy of the predicted Pareto front and then ladder. But also we have higher accuracy in the interpolation method compared to the naive interpolation. To wrap up everything, the proposed method uses content features to estimate the knee of the curve at each resolution for each sequence. Spatiotemporal features are extracted first in order to predict the knee points, the knee QPs, and then we follow a sequential prediction of the knee QPs starting from the highest resolution down to the lowest. At each step, we apply feature selection and particularly recursive feature elimination. Next, we train and test several machine learning regression methods, including support vector machines and with different kernels and random forests. But what we found most suitable, what gave us best results, was applying Gaussian processes. And that seemed to perform to give us the best, let's say, prediction of the knee points. To avoid, of course, overfitting, we applied a 10-fold random cross-validation process. After we get those predicted, let's say, QP that correspond to the knee points, we do some probe encodes within the range we defined with those knee points. So for the evaluation, we employed the same data set of 100 publicly available UHD video sequences as we did for our previous work. Those sequences have a native resolution of 2160p with a chroma format 4:0 and a bit depth of 10. The frame rate for most sequences is, for the majority of the sequences, is 60 fps. Each sequence contains a single scene. We don't have any scene cuts. And as you can see, we have a variability of object scenes and regions of interest, camera motions, and so on. In this paper, we considered scaling across 4 resolutions, so 2160p, 1080p, 720p, and 540p. And we used, to do that, we used the Lanczos-3 filter for both downscaling and upscaling. For defining the bitrate ladder range, we considered a bitrate range typical for video streaming from 150 kilobps to 25 megabps. We evaluated the proposed methods by computing, as usual, the BD metrics. And we also defined a metric that is related to the number of times we hit identical points on the Pareto front as the reference ladder method produces. So for the benchmarking, we consider, of course, the reference ladder, where all sequences are encoded at the QP range from 15 to 45 with a step of 1. We considered the naive interpolation ladder using 7 equidistant QPs, because from our previous work, we've seen that this produced the best results in terms of BD rate. And then for the proposed method, we used 4, 5, 6, and 7 points of QPs for the probe encodes. For the shifting of resolution, we used different steps, like, for example, -8 for the top 2 resolutions, 8 and 10 for the lower ones. We came up with these numbers after a thorough testing of different combinations and by testing which one produced the best results. We also compare this proposed method against our recently published method that uses features to predict the VMAF rate intersection points, the cross QPs as we call them, which are another, let's say, interesting characteristic of the Pareto front, which actually represents, the cross QPs represent the intersection points of the curves across the different resolutions. So by training the model, what we have is the predicted versus the predicted knee versus the true knee across different resolutions. As you can see that then the numbers, the R-square and mean absolute error and the correlation values are not, let's say extremely high. However, this is good enough to guide our interpolation. In this figure, you can see the distributions of the BD rate of the 3 tested methods, as well as the complexity versus the accuracy trade-off. As you can see, the CIL method appears as the best compromise between all these methods and achieves a significant improvement in terms of required maximum number of encodes compared to the naive interpolation-based method or the FL method. What it is also important to note is that for a reduced number of encodes, we can achieve a really high percentage of identical points with the bitrate, with a reference bitrate ladder. Here are some examples of the bitrate ladder produced, and as you can see, in most cases, the CIL and NIL methods are closer than compared to the FL, which seems slightly shifted compared to the reference ladder. To conclude, we have proposed a content-driven method that uses the highest curvature points of the VMAF rate curves to guide the interpolation. And overall, the method achieves, for a small BD rate cost, a really good, significant reduction of complexity. In the future, we plan to further explore this method and add also other parameters like frame rate and bit depth. Thank you very much. I'm ready now for questions.